So the second issue is we correct for two of the major issues associated with error in the balancing accuracy issues. And that's between back pressure is one I'm going to show you, but the big one is really variance between diffuser types. That is the largest source of error that we see in the measurements. The third and not least item I want to talk to you about is a new method for balancing called predictive balancing. And it was implemented in the Smart Air Hood application software, and it takes the guesswork out of balancing a room. So there's some, again, it was designed for a single technician to be able to operate. So we started with that premise, and it's a lightweight, very maneuverable hood, as you can see, compared to anybody who's not familiar. The old hoods are quite large and bulky to move about. It's ergonomic. There's less strain on your back because it mounts on a pole, as you can see. So just to show you, and you would take this right up to the ceiling. This rod is extensible to 12 feet. There's a smartphone attached to this device that actually connects by Wi-Fi direct right to the hood. So the hood is actually a Wi-Fi direct connection. It's good for 200 yards. Bluetooth's about 200 meters. Or, I'm sorry, 20 meters. I said that wrong. It's self-supporting, as you can see in the picture. So you put the hood up into place, press the base handle into position, and the technician can walk away and go do what he needs to do, adjusting dampers and doing balances. The other thing that's come up more recently is issues around safety with balancing. So there's a lot of concern about climbing ladders. California in particular has called us on this, and it's become a bit of a hot topic that our device with that 12-foot pole and with your arms you can reach up as much as 20 feet. With the pole, it reduces the need for ladders and scaffolding, which reduces the risk associated with balancing. And this is my favorite. This is a balancing technician sent this into our blog. And he's literally about 25 feet in the air here, and I heard this guy's 7 feet tall, so that helps too. But he said this measurement would have been virtually impossible to make in other conditions. He's actually got a horizontal grid up caught in a louver, and he's reaching in there and making a measurement. And he's using the app on the phone. He's actually, you can't quite see it, but he's holding the phone and looking at it while he's taking the measurement. And again, this emphasizes the point, to our surprise, we're getting a lot of blog entries and people are sending us, showing us applications where the hood's used, and things we didn't even think of, where it can go places no ordinary hood can go. The next topic I want to talk about is compensation by diffuser type. So this is a first on the Smart Air hood. And no other hood at this point can actually do this. So standard air hood, airflow hoods do not correct for diffuser type. They're literally calibrated on a single diffuser. When you change diffuser type, all bets are off. So balancing is very difficult when you have mixed diffusers. As many of you know, it's common now to see slot diffusers along windows in the same branch with ceiling diffusers. It can make balancing very difficult if there's inaccuracies between the slot diffuser and the ceiling diffusers. So this is a sample. I'm going to show you a sample of some diffusers in our library. So on the smartphone application, we've included a library of diffuser types. We currently have about 70 diffusers loaded into that device. And I'm going to show you what those look like in a second. So this is a lab we built. It's a precision air calibration station. We built this to an extreme point because we knew that what we were doing was fairly revolutionary. We wanted to make sure we could stand behind our claims. That 0.028%, the standard hood is 3%. So we're better than 10 times more accurate in this calibration station than the hood's requirement, even for their accuracy. And what I'm about to show you is we've taken, I think I had them here, this series of diffusers. I wanted to show you this. So this is a sampling from our diffuser library. So these are common diffusers you see out in the market. And I'm showing you several here, including a slot, a laminar. And we took these diffusers and several others, we put them on the end of this lab down at the far end, and then we took a standard hood, something out on the market today, put it on the end, took careful measurements across the range, and right after that we took a factory calibrated Smart Air hood, like this one, and mounted it and ran them back to back. Let me show you what the results look like. So this is a standard air hood run on that system. And what you're seeing, the black lines represent the actual accuracy curve. We're running from 75 CFM to 400. That's kind of the normal range of any office diffuser. You'll see them within that range. The scale on the right, if you can't read it, is up to 35%. It's pretty well known in the industry. The TWR is a swirl diffuser. Standard hoods have a very difficult time measuring those accurately. I think the one that troubles me and causes the most difficulty is a 2x1 slot diffuser. It's up there in the 15% range. Again, those are mixed in with standard ceiling diffusers. The device does pretty well with standard diffusers, but when you mix those together and you're trying to do a proportional balance, that can really mix things up because you've got different accuracies and severe inaccuracies going on between the diffusers. So now I have to explain what we actually did. We took these errors, we took this hood and calibrated on a four-way diffuser, and we call that the reference. That reference is calibrated on every hood. So when you take the hood out and you put it on a four-way diffuser, that's the total reference. It's linear and accurate. When you go to the app on the phone, we've loaded in error curves, and we lay those error curves over the base curve. And so we end up with a nice linear result. So this is the standard hood taken out of production, and we ran it at the same time. And this shouldn't be surprising. There's nothing mysterious about this. We characterized every diffuser to make it fit within that line. I would argue I could take a washing basket, put duct tape around it, put a differential pressure sensor on it, and I can make it do that because our system's designed for characterization. So we can fit just about anything in between the lines. When you read that app on the phone, you're laying it over the base curve, and we're compensating for any errors that we see. So our device is accurate within the tolerance on any diffuser in our library. I said we have 70 right now. If you're out on a job and you find a new diffuser we haven't seen, we get these every month now. Send us the information on that diffuser. If you have a hood, we'll purchase one, we'll put it on the rig, characterize it, put it on our app, load it up in the store. When you download, go and update your app at the Android store, you'll upload those diffusers. I would guess at the rate we're going right now, in 2 years we'll have 300 diffusers on this system. So I just explained that, but I'm going to walk through it just real quick just to say it again. We calibrate every hood, as I just described, to a standard four-way diffuser. All the diffusers in the library are characterized on our precision calibration lab, and the error curves for each diffuser are stored in the app. And then when you pick a diffuser off the library, it loads that characterization curve over the other curve and corrects, so you get that nice linear output. Does that make sense? We get a lot of questions on this. So I'm going to talk a little bit about back pressure, one other source of error, and it's actually where we started 3 years ago when we started working on this device. And just so you understand, so back pressure is when you install the instrument, the ducts are open, you've got all the dampers opened. You install the instrument, any resistance to flow is going to cause the flow to go back in the system out the other diffusers. So we call that back pressure. We resolved that problem through an aerodynamic design. We call it quad flow. It's a structure in 4 channels on this device. And it's designed to create a non-destructive path for the air to flow out without resistance so we don't create back pressure. This was all developed on CFD computer modeling, computational fluid dynamics, and that helped us reach the ultimate goal here. I'm going to show you some models. This is a standard hood from a while ago. 3-cone diffuser, nothing unusual. When you see the vectors going back up in the flow, that's creating back pressure. These are velocity vectors of the airflow, and you can see they're swirling around and going back. We really don't want that to happen, so that causes back pressure. If you watch this hood, it's a simulation of that hood, you can see the flow smoothly moves out undisrupted through the 4 ports. There's nothing going backwards. We measure the 4 ports, we sum the 4 areas of flow, and we get the total flow in the system. Not too bad on a 3-cone diffuser, like I have up in the corner. I want to show you a single directional diffuser, 2x2 single directional. These are notoriously bad. Lots of balancers know that you have to get a K factor to be able to use these on those types of diffusers. But you can see here how much swirl is going back up into the flow. So there's a lot of back pressure created by the system. Because we measure each port, we can just sum up those 4 ports. All the flow is moving out. There's very little back pressure caused in this scenario. So the third item I wanted to talk about, unless there's any questions on that, Those are, I think, a little straightforward. This topic's not. So this is predictive balancing. This is a new way to air balance. And this came out of studying all these things over a period of the last 2 to 3 years, and we found a way to resolve and determine how to balance a system. I'm sorry. I'm going to tell you, for those that don't know, I'll explain, if I can, and briefly what proportional balancing is. That's the method that's used today. So it's based on an iterative process where you adjust the proportions of the devices you want to measure to a key. So maybe I can walk through it. You open all the dampers, swing and take a measurement through all the devices, all the terminals. Find the one closest to the measurement, that's your key. You leave it open, you go to the next terminal, you measure it, you try to come up with a proportion to the target you want to hit, and then you may have to move back and forth between the key and that device until you bring it into tolerance. And then you move to the next diffuser. So it can cause quite a complex system, and very experienced technicians that do balancing do manage this quite well. If there was a method that could optimize the flow for each terminal and actually predict it, which is why we call this predictive balancing, it would be much more efficient, easier, and it would take less time and skill for the operator to actually balance the system. And that's exactly what we did. Predictive balancing is what we call this because we predict the flow from every diffuser as we move along. It's an iterative process, and as you go from diffuser to diffuser, we tell you exactly where to set it. One sweep through the system, and the system's balanced. So I'm going to read this because this was our definition. It's based on mass flow and energy conservation methods. Predictive balancing technique predicts the ideal flow set point for each terminal under adjustment, such that every terminal is at the target flow when the process is complete. I'm going to try a little more. It's just to give you a little flavor for those of you, there's probably some air balancing geeks out here somewhere that would be interested in this, but predictive balancing is a set of sequential equations that determine the effect of changing one damper on the flow of all the other terminals in the system. With this information, we can determine the optimum flow set point for each terminal after the previous terminal is adjusted. We also calculate the effect of each change on the blower output, and we optimize to a theoretical perfect balance. So in a perfect world, the numbers that we show on our app would be a perfect balance. It's not a perfect world, but it actually works better than we even expected. So maybe some graphs make it a little easier. This is proportional balancing. You sweep all the terminals with the dampers open. Go through, you kind of guess at a point where you're going to set the damper. You check it against the key. If it's off, you go back and do it again. Then you move to the next diffuser. You take that one and try to balance it against the key. You're actually adjusting. There's no particular science to this. You sort of, the experienced people know about where to set that to get it close so they can bring it within tolerance. When they're all done, they go through and make all their readings. If they missed on the tolerance requirements, they go back and do it again. This is predictive balancing. Same flow chart. Sweep the system, set the flow to the target, set the flow to the target, set to the flow to the target, read them all, and you're done. You're literally just a linear run through the system. So we built all of this into something we call Predict Air app. It's on that phone. It ties to this airflow hood, and it's all automated, so you can use this on any balancing operation. So it's a series of screens that actually walk you through the entire balancing process. It tracks everything, and it even delivers a report out at the end that shows you every step you made along the way. In general, we found that this works on almost any application. About 4 months ago, I balanced the system with 26 diffusers in one branch. No trouble at all. So the program calculates the optimum set point for each terminal and tells the technician exactly where to set it, where it lays up in the ceiling. He sets it to that point and then moves to the next diffuser. That's all there is to it. The data is stored on the smartphone, and it can be uploaded to a computer or emailed in any way out of that smartphone. It's a CSV format, so you can load it into Excel. So I won't say these are very scientific. First, I'm going to take a little disclaimer here, but we went to a very simple balancing job. We got 3 window slot diffusers, 3 ceiling diffusers. We just wanted to try to understand timing. How does this work? What does it mean in a speed test? So we had one technician balance this using predictive balancing in the smart air hood Took him 13 minutes to balance the system. We had another technician, they went back, kind of randomly reset it and balanced it again, and it took them nearly a half an hour for 2 technicians to do the same work. Again, not real scientific, but that was our first indicator of the speed improvement. And I'll show you why it's so much faster in a second. Accuracy, this is what the proportional balancing team came up with. Not bad, they're just in target there. It's usually plus or minus 10%, so very close. The reason the numbers are off a little bit is because, again, they have to guess, and if they get close when they're doing the iterations between the key and the terminal under adjustment, they stop and they move on. We didn't let them do any iterations in this. So they did pretty well, actually, to get 10% with no iterations. And this is the predictive balancing team. So because it's automated by the machine, by this computer, and the points are optimal. Actually, very nice results, 4.5. But this is just the data we collected. Again, it wasn't a real scientific study, but it shows some of the capability of the system. We normally see less than 5% when we balance any system using predictive balancing. This plays into productivity, and this means a lot to balancing contractors. So because predictive balancing, again, there's that linear flow depicted here, proportional balancing, the previous version, with its cycles and iterations. But in a nutshell on the bottom, if I had 6 terminals, like the system I just showed you, the minimum and the maximum number of steps for predictive balancing is 5. N minus 1, set all terminals, you're done, when you're actually doing that balancing operation. Proportional balancing is twice as many steps because you have to go from the terminal you're adjusting back to the key and then back again to the next terminal, so you're going back and forth. We just run straight through the whole system. If you do any iterations, of course, the number of steps is unknown. It could be many more than that if any iterations are required. If you'd like to see a live demo of this predictive balancing, I tried to describe it here in screens and waving my arms a little bit. We're actually running live demos and balancing down at our booth at C4124. We actually run predictive balancing. We show you all the features that are built into this hood. And we've actually built a portable office down in our booth. It has 4 diffusers and a blower with dampers. And we'll actually take you through and do a balance, or I think we're pretty much ready to let people do it themselves at this point. So we set it up. You tell us what flows you want out of the diffusers, and then we sweep through the room and actually balance it live.